Hi everyone, this is Arpan, and the video that you are about to see is for CS1, Chapter 3, Part 1. It's related to joint distribution of variables, and I think that is a very important topic. So, in part of our effort to provide freshers with all the required courses. So this is our effort where we are going to record CM1, CS1, and then the R, VBA, and Excel. So out of that, CM1 course is completed. It has been recorded. It is complete. CS1, it has also been recorded and it will be added in time. CS1 is the beauty about CS1 is created by one of my old friend Shweta, and currently she is part of Sun Life. So initially she used to report to me, and then when I left Sun Life, we still had that connection, and she will be recording the CS1 course, and obviously under my supervision, and I'll be recording few of the last chapters if that is needed. And also the R section. The R section will be completely recorded by me because I'll be doing it for both CS1 and CS2. And then Excel course has been recorded. It is one of the most advanced course that I have recorded. In my Blue Dragon Universe website, I think more than uh, along with the trading courses, I don't think there is any other course that is more advanced than Excel. It's a super advanced course. So if you have not registered for it, please do register. If you are willing to kind of uh, go past beyond your peers in Excel, right? And yeah, soon we are going to bring VBA and R, and maybe somewhere in this year. I cannot commit the date, but of course, depending on how my schedule pans out, I think somewhere in this year we are going to work on SQL as well. So this is the time that will be slowly moving from Actuary towards the artificial intelligence section, and whatever is needed for artificial intelligence, we are also going to part of it. So remaining part of the video for CS1, and do follow our LinkedIn page, our Instagram page. All the links will be in description. Visit our website, and yeah, I hope that you can see the quality of these courses from the videos that is present in this channel. And if you're seeking knowledge in actually in coding in artificial intelligence, then this is one website that you should follow. And I hope that you are going to purchase our course, and of course benefit yourself by doing in the process. So that's it, and let's enjoy the rest of the video.
Hi everyone. Our today's topic is joint distributions. So till now we have considered situation containing only one random variable. In this chapter we will consider results involving two or more random variables. Like earlier we were studying either x or y. Now we will study x and y together. So firstly we will study or define the joint probability distribution functions. Then we will see how we can obtain marginal distribution function from the joint distribution functions, and then the conditional distributions. And then we will also find out the moment generating functions of the joint distributions and the mean and the variance. So basically, where are joint distributions used now? Now, you might have heard that the spouses take the policies, life insurance policies together. So that is where we use the joint distributions of both the individuals together in order to compute the joint probability. So in this chapter, we will first study the joint distributions, then the marginal probability density functions, then the conditional probability distribution function, then when are the variables said to be independent, then we will calculate the mean, expectations of the product, sum, and convolutions where we will use general formulas. And then we will use moment generating function to derive the linear combination of independent random variables. So let us define joint PDFs first. So it is represented by, in discrete cases, it is represented as probability x is equal to x or y is equal to y. You can write it as probability x is equal to x, comma y is equal to y as well. So this is the joint probability distribution of two random variables x and y. In continuous cases, you can write it as f x y, the joint distribution of x y. Fine. These are the joint distributions. Now we will study from these joint how to calculate the marginal ones. That is probability x is equal to x or fxx, right? We will also look into how we can compute the conditional distributions. That is probability of x is equal to x given y is equal to y in discrete case, or in continuous case we can write it as function of xy x given y. Okay. Then we will look into the covariance and correlation coefficient of joint distributions also. Right? So let us start with joint distributions. There could be many variables involved, but first we are looking into bivariate cases. Bivariate is the one which involves only two variables. So we are taking x and y as the two variables. So first let us look at one discrete case. Let us consider two random variables x and y such that x can take any value from 1 to 3. Similarly, y can take any value 1, 2, 3 and 4. And the probabilities are given like this. Like the probability of x1, y1 is 0.1. x2, y1 is 0.1. It is 0.05. Again, it is 0.15, 0.1, 0.05. This is 0.2, 0.05, 0, 0.15, 0.05 and 0. Now the summation should be 1. Okay, because the sum of probabilities is always 1. You can verify it also. Summation of x, summation of y, probability x is equal to x, y is equal to y should be 1. Fine. You can verify this as well. Now, okay. Now let us find the answer of probability x is equal to 3, y is equal to 1. You have to just go through this table. X is equal to 3, y is equal to 1. You will get the probability as 0.05. Similarly, x is 1, y is 3. X is 1, y is 3 is 0.2. So they could not be the same every time. Fine. So what does this joint probability signifies? X is equal to x, y is equal to y. In discrete cases or in continuous cases, I can write it as fxy, xy. So this specifies how the total probability of 1 is divided among the possible values of x and y. And thus they give the probability distribution of xy instead of x and y individually. Right? In the continuous cases, I can write it as, now they have two conditions which are to be met. First of all, the probability distribution should be greater than or equal to 0 for all x and y, because this is the case for probabilities, and their sum fxy should be 1. This is what we have done for single random variable also. Fine. Now let us take one more example. Let us consider let us consider two random variables m and n, where probability of m is equal to n is equal to n is given by m upon 35 into 2n minus 2, where my m can take the value 1, 2, 3, 4 and n can take the value 1, 2, 3. Now we have to calculate probability m is equal to m, n is equal to n for all m and n. How you will do this? Let me give you one example or solution for this value. Try calculating probability m is 1, n is 1. What will it come out? Put M as 1, N as 1. It will come out as 2 by 35. Now try calculating the value of M is 1, N is 2. Fine. So calculating on a similar lines, you will end up with a table like this. Here are your values of M: 1, 2, 3 and 4. Here are your values for N: 1, 2, 3. If you will calculate, you will get 2 by 35, 4 by 35, 6 by 35, 8 by 35. Again, the sum will be 1 of all the probabilities, joint probabilities. 1 by 35, 2 by 35, 3 by 35, 4 by 35. 1 by 70, 1 by 35, 3 by 70, 2 by 35. Let us extend this example a little. What if I ask you to calculate the probability of M is equal to 3, where N is 1 or 2? Now they both are independent cases. In short, you have to calculate the probability M is 1 and M is 3, N is 1, plus M is 3, N is 2. What is the probability of M3 and N1? It is 6 by 35. M3 and N2, 4 by 35. You will end up with 10 by 35. Fine. M3 N2, sorry, it is 3 by 35. Similarly, what if I ask you to calculate probability of N is equal to 3? You will simply add up these probabilities. Fine. What if I ask you to calculate the conditional probability of M is equal to 2 given N is equal to 3? What is probability A given B? Probability A intersection B by probability of B. You know probability A given B is probability A intersection B, probability of B. So here it will be probability M is 2, N is 3 upon probability N is 3. What is M is 2, N is 3? 1 by 35. And you have already calculated probability of N is equal to 3 here. Right? So this is a simple example of discrete case. Let us move on to continuous cases now. Now how we will calculate joint PDFs in case of multivariate or bivariate variables? So we will use double integral instead of single integral now. So now there are two random variables in continuous cases. X, which lies between x1 and x2. There is another random variable y, which lies between, let us keep it same, y1 and y2. So I can write my probability, my x is less than x1 but greater than x, lies between x1 and x2, y lies between y1 y2. It should be similar to joint distribution or double integral of y1 to y2, x1 to x2, fxy dx dy. Fine. How is the joint distribution will look like now? Joint distribution will be capital F xy, right? So it will be probability x is less than equal to x, y is less than equal to y. Fine. Now how can you calculate probability distribution from the joint distribution? What is fxy? It is the differentiation of capital Fxy, that is del square by del x del y capital Fxy, joint CDF, right? You can integrate the PDF to get the CDF and you can differentiate the CDF to get the PDF. Now again, there will be two conditions here also. that fxy should be greater than equal to 0 for all xy because these are the probabilities, and integration over x, integration over y, fxy dx dy should always be 1. Fine, because the sum of probabilities should be 1. This is similar to one variable case in which if we talk about only variable x, we know integral over x, fx dx will be 1 and fx will always be greater than equal to 0 for all x, right? So it is going parallel to the single random variables only. Let us look into one question for continuous distribution. You have been given the joint distribution of two random variables u and v, fuv, as 2u plus v upon 3000, where my u lies between 10 and 20 and v lies between -5 and 5. Okay, you have been asked to calculate probability that u lies between 10 to 15 and v is greater than 0. So it says that it shows that we will use double integral. You can write it as u is from 10 to 15, v is from 0 to 5 because the upper limit is 5. 2u plus v upon 3000 into du into dv. Now you can first integrate with respect to u, plug in the values of u. Then you can integrate with respect to v and plug in the value of v. On solving it, you will get the answer as 0.229. Fine. So this is how our joint distribution looks like and how they are being applied. Now let us look how to calculate the marginal distributions from the joint distributions. Please look into it carefully. It is an important topic. Marginal PDFs. First, we will look in discrete cases only. Now I have been given the joint distribution, that is fxy. I have to calculate the distribution of only x or y. So that is known as marginal PDF. So I can write the marginal PDF of x as fxx, and I have been given the joint distribution fxy. So if I sum my joint distribution over y, I'll get the marginal distribution of x. Similarly, if I have to calculate it for y, I'll sum it over x. Fine. We will look into its questions also. Let us look into the similar example we saw earlier. I have been given probability m is equal to m, n is equal to n as m upon 35 into 2 to the power n minus 2, where my m ranges from 1 to 4 and let me write it down only. N ranges from 1 to 3. Now, if I have to calculate probability m is equal to m, what is the formula that I can use based on this? It will be summation over n. N is from 1 to 3. Probability m is equal to m in n is equal to n, right? So I can write n is equal to 1 to 3 m upon 35 into 2n minus 2. So answer will come in terms of n. Start plugging the values of n as 1, 2, 3 and add them up. If I put 1, it will be 35 into 2 to the power minus 1. If I put 2, it will be 35 into 2 to the power 0. If I put 2, it will be 3, it will be into 2 to the power 1. Right? On solving this, you will get that it is n by 10. Similarly, you can try computing the marginal distribution of n. Now it will come in terms of n and you will plug in the values of m from 1 to 4. Right? So this is how the marginal distribution is calculated in discrete cases. Let us look into continuous cases now. There we were using summation. Here we will use integrals. So fxx, there it was summation over y, here it will be integral over y. Right? Let us take the similar example. We have been given f u v, u comma v is 2u plus v upon 3000, where my u ranges from 0 to 10 to 20 and v ranges from -5 to 5. Let us find the marginal distribution of u first. I can write it as integration over v is equal to -5 to 5, 2u plus v upon 3000 dv. So I have to integrate with respect to v. Let me take 1 by 3000 outside. It will be 2uv plus v square by 2, where my v is -5 to 5. Now put the values of 5 and -5 here and start solving it. You will get u by 150. Fine. Where my u, now you have to write the condition also, where my u will always lie between 10 and 20. Similarly, you can simplify and find it for v as well. You will find it will be 30 plus v by 300, where my v lies between -5 and 5. So this is how we treat the continuous cases. So now we have studied joint distribution function and how to calculate the marginal from them. Now let us look into the conditional distribution functions or conditional probability functions. We know that the conditional probability function of probability A given B is written as A intersection B or B. Probability of B. You can write or comma here also, right? So now let us look into discrete cases. In case of discrete cases, if I have to calculate probability of x given y is equal to y, xy, it can be written as probability x is equal to x given y is equal to y. Based on this, I can write it as probability, that is a joint probability of xy upon probability y is equal to y, right? This is for discrete cases. In continuous term, I can write it as x given y is equal to y, xy. It will be same. Fine. Let us look into one question now. I have been given fxy as 1 by 16 x plus 3y, where my x and y both ranges from 0 to 2. I have to calculate the conditional PDF, probability of x given y. So what is the conditional PDF? How does it look like? It is the joint PDF upon Fy, right? Let us find Fy now. Fy is the marginal PDF, and since it is a continuous case, so we will use integral over y. Y ranges from 0 to 2, 1 by 16, x plus 3y dy. Fine. Since I have to calculate it for y, I have to use the limits and variable for x only. It will be x squared by 2 plus 3xy, where x ranges from 0 to 2. On solving this, you will get 1 upon 16, 2 plus xy. Now plug in the values here. It will be 1 upon 16 x plus 3y upon 1 upon 16, 2 plus xy. So what will it come out to be? It will be x plus 3y upon 2, 1 plus 3y, where my x ranges from 0 to 2. Now here I've written only for x because I have to calculate the conditional probability distribution function for x based on y. Now let us look at the independence of random variables. Please write it down. Two random variables x and y are said to be independent if the joint distribution of fxy is equal to the product of their marginal distributions. Fine. That is, the joint PDFs is the product of marginal PDFs. So in case of discrete distributions, I can write it as probability x is equal to x, y is equal to y should be equal to x is x into y is y. Then x and y are said to be independent. In case of continuous distribution, I can write it as x1 less than x2, comma y1 less than y2 should be the product of x1 less than x2, y1 less than y2. Fine. Now there is one result. Please write it down. If random variable x and y are independent, then their functions will be independent as well. What I mean is, if x and y are independent, then the function of x, say f gx, and function of y, like hy, they both will be independent as well. So this is a result. Fine. Let us look into one question. It says that consider the joint probability density function xyz given by fxy is given like this. Verify that the random variables xyz are not independent. That is, the joint PDF of xyz is not equal to the product of their marginal PDFs. But the random variable x and z are pairwise independent. That is, the joint PDF of xz is the product of x and z, and yz is the product of y and z. Let us show this. Let us solve this question. I have to show that they are not individually independent. XYZ, they together are not independent, but XZ and YZ are pairwise independent. The function that was given to me was z is greater than 0 and this is 0 otherwise. Okay. So if I'm being given with XYZ and their joint PDF and I have to calculate the individual PDFs, so obviously I have to first compute the joint PDF of XY and then XZ and then YZ, right? So first compute the joint PDF of X and Z. So for X and Z, I have to integrate it with respect to Y. You can write it as XY plus Y square by 2 e to the power minus Z, where my Y ranges from 0 to 1. You can calculate it as e to the power minus Z X plus half. Fine. Similarly, you can calculate the joint PDF of YZ. It will be e to the power minus Z Y plus half. Now using this, you can calculate the individual or marginal PDF of X and Z, and then you have from here you can calculate the marginal PDF of Z also, Y also. Now let us compute the marginal PDF of X. We will integrate with respect to Z now. On solving this, you will get X plus half. Similarly, you can calculate the marginal PDF of Z, that will come out to be to the power minus Z, and the marginal PDF of Y will come out to be Y plus half. Now multiply these three. I mean calculate Fx into Fy into Fz. It will be X plus half into e to the power minus Z into Y plus half. Fine. This will never come out to be same as this. X plus y e to the power minus z, because obviously I'm having two halves also. This is not equal to x plus y. So x, y, z are not independent. But if I take fx, fz, I will get e to the power minus z x plus half. This is same as fxz. Fine. Fine. This will be same as fxz. So they are pairwise independent. Similarly, fy, fz will come as fyz. Fine. So they are pairwise independent.